We started talking really about gases. I don't think we got too far into it, but obviously when we're talking about gases here in the state of matter, that is when we have pretty much completely broken apart everybody from each other. They are flying around, and it is as they are flying around and they do make collisions that we associate with the pressure of a gas. And one thing obviously is as the number of sort of collisions increases, so usually does the pressure. And obviously vice versa there. If we sort of lower the number of collisions, we will obviously see a lowering of the pressure. So I think last time we started just talking about things that are normally sort of found as gases. So obviously a lot of those sort of diatomic molecules that we talked about are elements. Like H2, O2, N2, Cl2, F2. These guys are gases under normal conditions. Obviously, are group 8 on the periodic table. Also, gases are neon or helium and all those guys. Those are monoatomic gases, which means they pretty much come as ones. So it's just like Ne, for example. In addition, we also, I think, talked about units of pressure, if I am not mistaken. And one way that we very commonly measure pressure is by using what is known as a barometer. And old barometers, again, used to be filled with mercury. And again, there would be sort of a glass tube inserted in it. And as, again, the atmospheric pressure sort of pressed down on that sort of pool of mercury, what would happen is the mercury inside the tube would go up or down, obviously, depending on the pressure. And typically on these barometers, if you guys still have one in lab or not, but typically you can just have a ruler that's on there and we take sort of a measurement of it. A lot of times it's in inches or centimeters, sometimes it's millimeters of mercury. And three very common units of pressure that we deal with a lot in chemistry is an ATM, which is an atmosphere, a torr, which is named after the guy who sort of invented the barometer, and a millimeter of mercury. And again, a millimeter of mercury is really just sort of a length measurement. And because usually in an old time barometer, it was actually mercury that you were sort of measuring. There is a relationship between all these three. And first off, though, a torr and a millimeter of mercury, they are basically a one-to-one relationship with each other. So if you ever has to convert between the two, you basically just change the unit. The number stays exactly the same. It's a one-to-one conversion between them. But if you want to go from an atmosphere to either of those units, one atmosphere is 760 torr or 760 millimeters of mercury. So that 760 number is a really important number that we use a lot to convert between different units. So obviously, if you have atmospheres and you wanted to kind of go into millimeters of mercury or torr, you're going to multiply by the 760. And again, that's going to give you either torr or millimeters of mercury, which is essentially the same. Obviously, depending on whatever unit you use there. And if you start with a torr or a millimeter of mercury and you wanted atmospheres, you're going to divide by 760. And again, a torr or millimeter of mercury, and that will get you your atmospheres there. So that sort of 760 number, definitely a number that we use a lot. As I think I mentioned at the very end last time, these aren't obviously the only units associated with pressure. So again, there's things like PSI, pounds per square inch. Pascals, kilopascals are very common units of pressure. Also, a bar is also another very common unit of pressure as well. I think that's sort of where we laid up, yeah? Any questions on any of that stuff? Okay, so we're going to see several different sort of gas laws as we kind of go through this part of the chapter. And really, when we're dealing with gases, there's usually sort of three different variables that we oftentimes sort of look at. And the three variables are pressure, volume, and temperature. So in a lot of cases, we will usually look at a number of gas laws, kind of at only two of these guys, and sort of keep the other one constant. There is a gas law that we'll see towards the end that basically looks at all three of them together. And basically what we look at in a lot of cases is if we change one of these sort of variables, how does it affect the other variable? If you have a pressure volume sort of situation set up, and you do something like maybe increase the pressure or decrease the pressure, we're able to sort of see what happens in terms of the volume of the gas that may be in that mixture. So let's take a look, I think, at the very first gas law, which is Boyle's law. And Boyle really studied the relationship between pressure and volume. And he held temperature constant. And Boyle's law, basically what Boyle saw was that if you have a volume that is really small, for example, let me just draw, I guess, a smallish volume. And if I got a bunch of gas molecules sort of in that very small volume, you would imagine that there's not a lot of space in there for those guys to fly around, which means we would expect a number of collisions to occur, just frankly because it's a very small space. So like a bunch of people in a very small space, everybody's going to be bumping into each other. Same idea here with the gas. There's going to be a lot more collisions that's going to occur in that very small sort of volume. The result of that is we should see the pressure start to increase as a result of that small volume. So what he actually saw was as the volume went down, we do see a increase in the pressure, again, because everybody's really smacked together in a super small spot. And he sort of found opposite of that was if, you sort of expanded the volume. Now, if you have, say, the same 5 circle gas molecules in there, there's a lot more room for those guys to fly around, which means it's going to take a little bit longer for collisions to occur. And the result of that is you will see the pressure start to come down because everybody's got a little bit more room to move around. So obviously everybody in here, a lot of room, we can move around pretty easily without bumping into each other or the walls and stuff like that. There's not as much pressure if we all just kind of shoved into a closet together, right? There's going to be a lot of collisions sort of occurring. So what he saw was as the volume went up, we would see that the pressure would go down. So that's what it means by a sort of inverse relationship. Basically, as one goes up, the other goes down and vice versa. And, a lot of times when you think about pressure and volume, sort of like what we talked about, I think when we were doing Le Chatelier's principle the other day, it's a good thing to just think about in terms of volume. If it's a small volume, there's going to be a pretty big pressure because there's not a lot of room for people to move around. One sort of relationship that it actually develops with Boyle's law is pretty much for any gas. If you take a bunch of pressure readings and volume readings, and you basically multiply them by each other, the two that go together, pressure and volume readings at different times, it will always end up being the same number. So there's always a sort of relationship, same number. So you'll sometimes see, like we talked about Boyle's law, P times V equals K, which is sometimes referred to as a proportionality constant. And basically what that allows you to do is, yes, sir. It's not K like an equilibrium constant. It's what's known as a proportionality constant. So it's a little bit different. It's basically a constant number. Yeah. So, and it's a constant number for a particular gas. So for example, if you did an experiment where you were taking pressure and volume readings for a particular gas at constant temperature, and you had like this number and this number for one reading, this number and this number for one reading, this number and this number for another reading. If you ended up multiplying the pressure and volume for every reading that you get, they all would be the same number. They would all equal pretty much the same number all the way down, no matter if the pressure was higher, because the volume will adjust based on the pressure. So a lot of times in gas laws, you'll see this little K sort of written next to it, and it just means that really a proportionality constant, which basically just means that because you could always take the pressure times the volume and equals the same number, you basically could set two different conditions up equal to each other. And that's essentially how we get to what is known as Boyle's law down here. And this is Boyle's law, which is P1 times V1 equals P2 times V2. This is sort of a before and after type of deal. So, maybe you have a pressure volume relationship. And like I said before, maybe you change the pressure and you can see how the volume would change accordingly. Or vice versa, if you have a pressure volume relationship and maybe you change the volume, you can see how the pressure would change accordingly to it. Now, in terms of units, it really doesn't matter the units of pressure on either side as long as they are obviously the same. So you can't have different units of pressure. They do need to be the same, but you could do any unit of pressure on each side as long as they are the same. And the same thing with volume. It could be the same unit of volume in each side. Doesn't have both has to, they both could be liters, they both could be milliliters, but you can't have a milliliter and a liter on opposite sides. Again, just mathematically speaking, it will not cancel correctly in terms of the units. So they do need to be the same. And again, this is occurring at constant temperature, this sort of relationship. So it's good to understand with these gas laws, sort of the relationship that occurs, for example, like in Boyle's law, that one goes up and one goes down. It can be very helpful when you do your calculations to make sure, your numbers sort of make sense. Sometimes people, it's very common in gas laws, they like inverse some numbers and kind of flip them around in the wrong spots. The temperature? Is there? Yeah, so you have to you have to have, for example, if you had a problem where they gave you a volume, say, of 100 milliliters, and then they gave you the second volume in like 0.2 liters. You can't use the liters and the milliliters together in this equation. Otherwise, just mathematically, they won't cancel. So for example, if I rearrange this equation and wanted to solve for P2 would equal P1 V1 over V2, dividing this to the other side, basically. Now, if I have on top, forget the pressure unit, but if I have on top milliliters as my unit, and I have on bottom liters as my unit, you're going to be off by a factor of 1,000. So you got to make sure that they're always the same units. And again, it doesn't matter what units they are, they just got to be the same. Yeah. So that's common. Sometimes you'll have different units. You just got to get them into the same units. That way, these won't cancel. But obviously, if you converted the bottom guy into milliliters, now you're good and it's going to cancel and you'll be able to solve for pressure. The other thing that we talk about with sort of gas laws is a lot of times you do obviously need to be able to rearrange these formulas. And, the simplest way to rearrange sort of a gas law formula is you could think of the equal sign. If he has to move some type of value across the equal sign, it always ends up in the opposite location. So you could think of them almost like fractions on each side. In this case, there really is no denominator, right? They're both like this. So in this case, I want to solve for P2. So it's technically on top. So when you move it across, it ends up on the bottom on the other side. So when you go across the equal sign in all these gas laws, the quick way to rearrange is basically everybody goes in opposite locations from where they started. So if they were on top, they end up on the bottom. If they're on the bottom, they end up on top if you kind of move them across. It's basically multiplying and dividing. Obviously, it's the other side. Any questions on that there? And this is a graph of really Boyle's law relationship. We have pressure on the Y and volume there on the X. And what we see is obviously here at a much smaller volume, we have a much higher pressure. As our volume starts to get larger, we do start to see the pressure decreasing. And obviously here at the larger volume, we have a much smaller pressure, again, just giving everybody a lot more room basically to fly around it. All right, so why don't we try one here, see our calculator, how it all works, hopefully. An inflated balloon has a volume of 0.55 liters at sea level, which is 1 atmosphere. It rises to 6.5 kilometers, where the pressure is 0.4 atmospheres. Assuming the temperature remains constant, what is the final volume of the balloon? So give that a go, see what you come up with. Let's take a look. So Obviously, in this case, we've only learned one gas law, but at some point here, we will learn several more. But sometimes it's a really good idea when you're dealing with gas law problems, really just to sort of pull out the information from the problem, sort of label it, and it oftentimes will point you sort of in the right direction in terms of what gas law you should use. So clearly, we have a volume that is 0.55 liters. It's at sea level at 1 atmosphere. So 1 atmosphere is a pressure here. It goes to 6.5 kilometers, which is frankly useless information in this problem. And it goes to another pressure of 0.4 atmospheres. And we're looking for a final volume here. So again, you could kind of really see, obviously, Boyle's law hopefully in there. And since it's the only one we talked about so far, that would be a great choice. Again, does it really matter which ones you call 1 and 2? It doesn't, as long as you keep, obviously, the numbers that go together. But usually people will just call the first set of numbers their 1s and the second set 2s. So here we're going to, once again, be solving for V2. So really, P2 is on top. So when we go across, we're going to divide it to the other side. It's going to end up there on the bottom. And that would give us V2 is equal to P1 V1 divided by P2. Now, in terms of units, we only have pressures on both sides here. So we want to make sure unit-wise we're okay. And again, in this case, we are. They are both in atmospheres. Once again, if one was in torr or millimeters of mercury, you need to convert the other one to the same unit. So we'll put our numbers in here, our P1, which is 1 atmosphere, our V1, 0.55 liters, divided by our 0.4 atmospheres. Here, the atmospheres on top and bottom will cancel. That's going to leave us units of liters for our value there. And roughly we'll go this way. 1.4 liters looks like a winner in that case. Any questions on that calculation? Now, if we remember, like we talked about, does sort of our answer make sense? When we look at the pressure, it started at 1 atmosphere. It ended at 0.4 atmospheres, which means in this particular case, our pressure has gone down, which means our volume should go opposite, right? Which would be up in this case. And it did. It went from 0.55 to 1.4. So again, our number does make sense. It's a good idea to sort of check that again, just to make sure you didn't invert a number. Yes, sir. I did. In this case, it looked like everybody had 2. So I ended up with 2. And pretty much all we did was multiply and divide in this case. Yeah. Other questions? So that is Boyle's law. Let us then maybe talk about another one here. The next sort of law we're going to talk about is our good friend Charles' law here. And Charles' law dealt with volume and temperature. And he actually kept constant here pressure. And his law is V1 over T1 is equal to V2 over T2. There's also another law that is very similar to that, which is Guy-Lussac's law. And that is like P1 over T1 is equal to P2 over T2. This is at constant volume. So Charles' law is at constant pressure. Our P1 T1 over P2 T2 is at constant volume. So let's first talk about what will happen in each of these situations. So let's start with Charles' law, which is our V1 over T1 is equal to V2 over T2 at constant pressure. So the way it's able to maintain constant pressure is essentially the volume will adjust to keep it at constant pressure. So looking at the guy on the right here, where we actually are at constant volume, if we had a situation where we had a rigid sort of container where the volume is constant, which is basically our P1 T1 is equal to P2 T2 situation. If I have gas molecules in there and I decide to increase the temperature by heating them, will those gas molecules fly around slower or faster? They will fly around faster, right? Light a match under somebody, right? They move a lot quicker. So if we increase the temperature by heating this, for example, we would expect these gas molecules to basically be flying around a lot faster. That should lead to less or more collisions. Yeah, it should lead to more collisions. And because the volume is pretty much fixed in place, there's no adjusting of that volume. And we definitely would expect to see the pressure start to increase as a result of that. So in this P1 over T1 equals P2 over T2 situation, where we have a constant volume, if we increase the temperature, we will have a lot more collisions because everybody's flying around a lot faster. And because the volume is locked into place, those collisions are going to continue to increase, and we will see an increase in the pressure. The opposite obviously would be true if we had our volume that was locked into place and we had our gas molecule. I'm just going to say ice in this case or something. We'll cool it down, right? So if we cool this sort of container down and lower the temperature, our gas molecule is now going to be moving a lot slower, right? So it's going to be flying around a lot slower, which means it is going to take longer for collisions to occur. And we would actually start to see less collisions occur. The result of those less collisions is we should start to see the pressure come down. So we would see the pressure come down in this case. So the relationship we sort of see with Guy-Lussac's law, which is P1 over T1 equals P2 over T2, where we have the volume pretty much fixed in place, no adjustment, is as you increase the temperature, because everybody's flying around faster, we will have more collisions. And again, because we have more collisions, we would expect the pressure to increase. And vice versa, if you lower the temperature, we would have less collisions because they're flying around a lot slower. And again, we would expect the pressure to go down. Any question on those relationships there? Now, if we look at Charles, yeah, I'm sorry. Yeah. No, so this is Guy-Lussac's law, which is this one, which is at constant volume. We're going to talk about Charles' law right now, which the volume isn't constant, but the pressure is constant. Yeah. So this relationship here, which is the P1 over T1, is equal to P2 over T2. That's the constant volume. And what we see is as temperature goes up, so is the pressure because the volume is fixed. And as the temperature goes down, so does pressure because the volume doesn't move to adjust. It is in this sort of relationship. So if the volume is constant, you would probably be looking at pressure and temperature. And if the pressure is constant, you would be looking at volume and temperature. Yeah. A little bit different, but yeah, these are very similar sort of relationships. It's just one looks more at pressure and temperature relationship, and one looks at obviously volume and temperature. So let's look at the volume and temperature relationship, which is really Charles' law. And Charles' law again is the V1 over T1 is equal to V2 over T2. This is the one where we do have constant pressure. So if we have sort of the same setup, and I'll just have my volume starting here, and I have my gas molecule here. When I start to heat it to increase the temperature, once again, it is going to start flying around a lot faster. It's going to cause a lot of collisions. Now, we saw the pressure increase in the last situation because the volume was pretty much fixed into place. But in this case, we actually want to have constant pressure. So the only way to do that is to pretty much give everybody more room to fly around it. So what happens in a Charles' law situation is as you increase the temperature, my volume decides, uh-oh, I better increase as well to give everybody enough room to fly around in. And what that will do is the volume will increase and it will be able to give everybody more room so that we maintain the same number of collisions. And if we're able to sort of maintain the same number of collisions, we are able to keep it at constant pressure because of that. So in Charles' law, what happens is, and the way it's able to keep constant pressure is the volume actually adjusts based on the temperature to give everybody the proper room to maintain the same number of collisions and keep the pressure constant. Same deal as well is if you kind of threw it on ice, if you will, or cooled it back down. As the temperature goes down, once again, our gas molecule is going to be moving around a lot slower. So what the volume is going to do is actually come down on it, squish it basically into a much smaller volume. So even though it's flying around a lot slower, the number of collisions will once again be maintained. And that is, again, how we're able to keep constant volume. So once again, we're able to maintain the number of collisions in the second case by kind of bringing the volume down. Do you have a question? Good. It doesn't in this case because the volume, by adjusting, allows the number of collisions to remain constant, and it's the collisions that really adjust the pressure up or down. So because the volume goes up, gives everybody more room, even though it's moving a lot faster to gas molecules, the number of collisions that is happening is pretty much the same. So that's what keeps the pressure. That doesn't happen in the previous situation because the volume is locked into place. So even though you raise the temperature, those gas molecules have nowhere to go. They're just going to be banging into the walls. And that's why we do see that increase in pressure. So Charles' law has a nice volume adjustment on it that basically is what allows it to keep the constant pressure. Any questions on either of those relationships? Okay. So another sort of important thing when we look at these gas laws, we could actually see from this sort of Charles' law graph, which is the volume versus the temperature in degrees Celsius. You could take any gas you like, bless you, and if you plot lines of volume versus temperature, and you do a nice straight line for each of those and bring them all back to the temperature scale, every single gas will hit exactly at the same number when it comes to the temperature. And that number is minus 273 degrees Celsius, technically minus 273.15 degrees Celsius. That number looks familiar. Hopefully that is the number we use to do what? That is exactly what it is. So if we wanted to convert this into Kelvin, we would add a 273 to it, which would give us 0 Kelvin. This is what is sometimes referred to as absolute zero. It used to be called the absolute temperature scale, later named after Kelvin because he did recognize the nature of this. And the good or bad news is pretty much every single gas law that you use, if you have temperature there, it needs to be in Kelvin. So 100% of the time, if you're doing a gas law and you got some type of temperature value, you do need to put it into Kelvin. And by the way, on this graph, we also see the same relationship we talked about at higher temperatures, larger volumes, lower temperatures, smaller volumes. Again, we get that volume adjustment with Charles' law here. So when we look at these two equations, and every single one from here on out that involves temperature, you do need to convert it into Kelvin. And again, obviously, our temperature in Kelvin is our temperature in Celsius plus a 273. This also means that a lot of people will screw up on problems like this because they will give you the temperature in Celsius. They will ask you to give the answer in Celsius. So it sort of makes sense. Well, like I give the answer in Celsius and they give it to me in Celsius. Why not just put it into the gas law in Celsius? And the answer is you will get the wrong answer. So even if they give you Celsius and ask you to give the answer in Celsius, when you go into the gas law, you got to put it into Kelvin and then convert it back to Celsius on the back end. So That's a very common problem. Textbooks is like Celsius. They give me the answer in Celsius. So people just go, I don't need to do that conversion step. So you absolutely do need to do it when you use the gas law. Then you got to do the conversion at the end to bring it back to Celsius. Any questions on any of that? Now, in terms of the volume for Charles' law there, once again, it could be any volume you want as long as they match on both sides. And the same thing with the PE1 over T1 equals P2 over T2. The pressure, again, can be any unit you want as long as they do match. Any questions on any of those laws there? All right, let's try one here. In an experiment, 452 milliliters of a gas is used in a light bulb that goes from 22 to 187 degrees Celsius at constant pressure. What is the final volume? Okay, let's take a look. And once again, now that we have a few different sort of gas laws to choose from, we got our Boyles, we got our Charles, and our guy Lusik's law there. That'll be a 1 equals P2 T2. So once again, if we sort of pull out the information here, obviously we have a volume that is 452 milliliters, and a light bulb that has a temperature of 22 degrees Celsius to a temperature of 187 degrees Celsius. And we were looking for a final volume here. So once again, just kind of pulling out the information, it definitely should lead you right here, as obviously we have no pressure. So that eliminates pretty much the other two in terms of what we need. Now, in this particular case, again, we could just call the first set of numbers 1s, the second set kind of 2s here, and we do need to convert our temperature into Kelvin. So we're going to do a 273 adding to each of these here. So that's a 22 plus 273 gets you 295 Kelvin. And also add a 273 here. You're going to get us 187 plus 273. Get you 460 Kelvin. In this case, we got V1 T1 is equal to V2 T2. In this particular case, we are looking to solve for V2. So really, we're multiplying to the other side, or if you just want to quickly do it, we need to move this guy basically up there to the other side. And that would give us that V2 is equal to V1 T2 divided by T1. And again, we're basically multiplying T2 to the other side to do that. Any questions on that there? At this point, we can plug in. We want to make sure we get our numbers in the right spots. So we got 452 milliliters. We are actually looking for T2 up on top. So that would be our 460. And we're dividing by our 295. Once again, here our kelvins will cancel. That's going to leave us only milliliters, which is good since we're looking for a volume. And that would get us 452 times 460 divided by a 295 there. Going to get us a volume of 705 milliliters in this case. Any questions on that calculation? Yeah. You can use the 0.15. It probably would be rounded off anyways at the end. So personally, I always go with the 273. It's technically 0.15, but most of the time that kind of gets rounded off. So most people do 273, but if you want to use the 0.15, you can. Other question? Yeah. Yeah, so in this particular case here, we have obviously 3 here, we have 3 here, and technically when we add this, we do get 460. And again, since I use 273 as a kind of a whole number, not the 0.15, that technically I guess would have 2. So I would take 705, or if you wanted to, 710 milliliters would get you to 2 significant figures on this. Yeah. Again, basically that does have 2. The way I wrote it there at the 460. Other questions? Yes, sir. If you need to solve for T2, Yeah, it is possible. Are you asking how you would rearrange it? Is that what you're asking? I'll get that 1 second. Let me just finish looking at this real quick. We want to make sure as well that, this does make sense based on sort of what we've been talking about. What we do see is our temperature did go up. So our temperature went up, which means we should assume that our volume would go up as well. And in this case, we did see that, right? It went from 452 there to 710. So we do see the correct sort of change. Now, your question is your question again, if you have that equation, you want to solve for the temperature, the second temperature. Yeah. So again, you could do sort of the quick move if you want. When you want to solve for something, right, it's got to be basically by itself up on top. So this guy needs to go to the other side. But that also means that everybody on the left-hand side there needs to go back the other way, right? So they both need to kind of cross back over. So if you do that, and we'll just do it in steps, if you move the T2 to the other side, you'll end up with T2 V1 over T1 is equal to our V2. Then now we need to move the T1 back over to the other side, which would give you T2 V1 is equal to V2 T1. And lastly, we need to bring the volume back down to the other side, which would be T2 is equal to V2 T1, and V1 here would be how you would rearrange it. You're basically would need to multiply both sides by T2, which so they cancel. Then you need to multiply both sides by T1 so that they cancel. And then you need to divide both sides by V1 so that they cancel, and gets you to where we just were. So that's really the math of what we're doing. Why I'm moving them with the arrows is multiplying and dividing everybody to the proper sides. If rearranging equations is a little bit difficult for you, you should take some time to figure out how to properly sort of rearrange it, because you will be asked, and you could be asked to solve obviously for anybody that is in the equation, obviously. Any questions on that there? Okay. So let us talk about one other law as well that we could kind of add to our list, which is our good friend Avogadro. He had a number, but he wanted a law as well. So when we think about Avogadro, right, we think about 6.022 times 10 to the 23 equals a mole is what we think about. So Avogadro's law, not surprisingly, involves moles, and it is V1 over N1 is equal to V2 over N2. And this particular one here is actually at constant pressure and temperature. So under Avogadro's law, under constant pressure and temperature, V1 over N1, N is the number of moles. So that is what N stands for, is the number of moles. And it's like pretty much any of the other gas laws, you can plug and chug and obviously solve for anything that's missing there. A relationship or a consequence of Avogadro's law is if you're dealing with some type of gas stoichiometry with an equation like so. I'll just say all these guys are gases. And if this sort of reaction should occur under constant pressure and temperature, you can, just like we would do in a mole to mole relationship, like we talked about, we could go, hey, there's 2 moles of A for every 1 mole of B, or 2 moles of A for every 3 moles of C, and so forth. You actually can, because moles and volume and sort of Avogadro's relationship are almost sort of proportional to each other. You could actually do a very similar volume to volume relationship like you would do stoichiometry. So we could say, for example, instead of 2 moles, that 2 liters of A would give you 1 liter of B. Or you could say 2 liters of A would produce 3 liters of C. So Avogadro's relationship is that basically as the moles sort of increase, the volume of the gas increases sort of proportionally to it. And you have sort of this volume and mole relationship that changes pretty similar to each other. As one kind of goes up, the other one goes up accordingly with it. And one nice thing about that is you could actually do some, if you ever had to do gas stoichiometry that involves gases, it can allow you not to have to use a gas law. You can almost just do a stoichiometry problem to figure out how much volume you would get. Any questions on Avogadro's law there? So all these gas laws here that we've talked to up to this point are sort of like a before or after, or something has been changed type of conditions. And really putting together all those gas laws that we just talked about gives us sort of the granddaddy of all gas laws, which is known as the ideal gas law. And the ideal gas law kind of pulls all these sort of concepts from all these previous ones that we've talked about. And the ideal gas law is PV equals nRT. And it is the ideal gas law that we use to describe ideal gases. And in case you're curious, an ideal gas is pretty much everything we sort of come across under normal temperatures and pressures. What makes something an ideal gas? There's really kind of 2 things that make something an ideal gas, as we will talk about a little bit later on in this chapter. But the 2 things that really make something an ideal gas is the idea that the volume of the gas itself is basically 0, considered 0 or negligible, compared to the container it's in. The volume of the container it is in. So that's why in a lot of gas problems, you will oftentimes see them talk about the volume of the container rather than the volume of the gas itself. So within a container, the volume of the actual gas is very, very small compared to the overall volume at which it's flying around in. And we consider sort of negligible under normal sort of temperatures and pressures. The other major thing that makes something sort of an ideal gas is the idea of, if you have a mixture of gases, there are no attractive forces or repulsive forces between gas molecules. So basically, if you got a bunch of different ideal gases, which are basically just gases under normal conditions, in the same container, even though they are flying around in the same container, we assume a fairly ideal situation where they pretty much are not interacting with each other. So they're not colliding with each other. You could almost think of, even though you got multiple gases in the same container, that they're in there by themselves, and the other ones are flying around in there by themselves. There's really no interactions in an ideal gas between different gas molecules basically interacting with one another. And those are really the 2 things that make something an ideal gas. If you continue to take chemistry, you will learn about things called real gases, which under really high temperatures and pressures, or low temperatures and pressures, I'm sorry, you get a lot of interaction between the gas molecules, and you do have to take those things into account. But under everything we sort of deal with, under normal pressures, we assume this ideal situation. So PV equals nRT is the ideal gas law, and it is different than all the ones that we've seen before. There is no like before and after. It is a one and done situation, one pressure, one volume, one temperature. It is also the most restrictive in terms of units. So when you use the ideal gas law, the pressure 100% of the time needs to be in atmospheres. So if you're going to use this equation, whatever unit of pressure you got going on, you got to get it to atmospheres. Also, volume, once again, here needs to actually be in liters. So again, whatever is given to you, if you're using this equation, you need to put it into liters for the correct answer to work. N is moles, so those hopefully should be in moles, I hope. And T is our temperature in Kelvin. So out of all the equations, this is a sort of no before and after, and also the most restrictive. And really the reason why all those other guys has to be in those units is because R is the gas constant. And the gas constant has a value of 0.08206. And it has all these units. It has liters times atmosphere up on top, divided by Kelvin times mole. Now, personally, I use 0.08206 because that's what they beat into my head, and I cannot get it out as much as I try. But lately and nowadays, people use a more rounded number a lot of times, 0.0821. You can use either number you like. I personally will probably use the 0.08206 most of the time. The good news is you always have this number available to you, but just to be honest with you, and like, you know, book problems and stuff like that, they don't tell you that. So you just got to remember it's sort of a constant number. It's always going to be that number, and you do always sort of have it available to you. I probably will obviously provide it to you. And the good news as well is if you're not sure what everybody else's units should be, that pretty much will tell you what everybody else needs to be in there, so everything cancels out correctly. Any questions on that there? So let's talk about another couple of important relationships involving sort of the ideal gas law and some other things. First off, we'll start with STP, which is in the middle there. STP does stand for standard temperature and pressure. And when they say a gas is at STP conditions or solved for something at STP conditions, they are actually giving you both a temperature and a pressure. The pressure at STP is 1 atmosphere. The temperature at STP is 273 Kelvin. So if you come across a problem where it says solve it for STP, those are the values you should use, pressure being 1 atmosphere, temperature being 273 Kelvin. They both need to be there at those values in order for it to be STP conditions. So if the pressure is not 1 atmosphere, then you're not at STP conditions. Or if the temperature is not 273 at the same time, you're not at STP conditions. There's a really nice relationship that you could use when you happen to be at STP conditions. And you could only use this relationship when you're at STP conditions. So when you're at STP, 1 mole of any gas will have a volume of 22.414 liters. So that is a nice conversion that 100% of the time you need to be at STP conditions to use that. And once again, if the pressure is not 1 atmosphere or the temperature is not 273, you cannot use that. What would be the benefit of using this conversion? The benefit of using this conversion is if you happen to be at STP conditions, you don't need to use the ideal gas law. So you can kind of bypass the ideal gas law and kind of use that conversion to get to an answer. If you are not at STP conditions, you need to use the ideal gas law. And by the way, if you are at STP conditions and can't remember that conversion, you could still use the ideal gas law, just put in there temperature 273 and pressure 1 atmosphere. So ideal gas law you can use pretty much for any conditions, including STP conditions, but this 1 mole is 22.414 can only be used if you're at STP conditions. Any questions on that there? And that's why, you know, we use an ideal gas law. It is very, very sort of a universal equation that we could use for a lot of gases. And like I said, under normal pressures, you know, it applies really well to most gases. Things don't really deviate much from it. By the way, that is how we actually get the value for R. And if you solve the ideal gas law for R, which is what they did down here, And they basically put in all of our numbers at STP, which means our pressure would be 1 atmosphere. We would have a volume of 22.414 liters, a 1 mole, and a temperature of 273.15. That is our 0.08206 number. That is sometimes used there for our R. Any question on any of those things there? All right, let's try one, I think. Calculate the pressure in atmospheres exerted by 1.82 moles of SF6 in a steel vessel with a volume of 5.43 liters and a temperature of 69.5 degrees Celsius. Let's take a look. So once again, if we sort of pull out the information here, we are looking for a pressure. We obviously have moles, 1.82. We have a volume that is 5.43 liters and a temperature that is 69.5 degrees Celsius. So you could probably see the ideal gas law there would be the best choice, since we also do not have 2 pressures or 2 temperatures or 2 volumes. We do just need to make sure some unit wise here. So moles is good. Our volumes already in liters, which is good. So much like most problems here, we do need to do our conversion. So that's going to give us, we'll do 342.5, I think, on that. 273 plus 69.5. All right, and that should be Kelvin, obviously, here. All right, so now we got everything that we need. We are solving for P, so we want to isolate it. So once again, basically everything's on top. So we're going to divide the V to the other side and put it on the bottom. That would give us P is equal to nRT divided by V. Remember, we always have R, which is our gas constant. And that means we're good to plug in. So we'll do our 1.82 moles, our 0.08206 liters atmosphere Kelvin mole, times our temperature, which has been converted into Kelvin, and all divided by our volume there, which is 5.43 liters. In terms of units, the moles on top and bottom here cancel. Kelvin on top and bottom cancel. When you divide, the liters will cancel. That will leave you just atmospheres that's left over at that point. And if we do all that good stuff there, looks like we do end up with a pressure of 9.42 atmospheres in this particular case. Any questions on that? Yes. R is just a constant, so it's a value you always have. Again, like I said earlier, they really don't tell you that in problems, so they just assume that you know you have that value. So, if you pull out the information like I did there and you're like, that looks like the ideal gas law, but I don't have R, you should have it, because it's always going to be that number, so it'll never change, and it's just sort of a value that's you just kind of have. Yeah. But again, very commonly, they don't put it in the problem, like, hey, R is this value or anything like that. Yeah. Other questions? Then let us talk about another gas law, because I feel like there's more room to talk about. So we can have a gas law that basically takes into account really all 3 variables that we've been talking about, which is pressure, volume, and temperature all together. And we could get to there really, and it's not that important for our class, but we could get to there by taking the ideal gas law and basically setting it equal to R, since R is a constant value. You can then put both of those guys together. And in most cases with a gas, if you don't open the lid, the moles shouldn't change, right? They shouldn't be able to escape if they're in there. So those guys will also be constant. And this gives us what we commonly like to refer to as the combined gas law, which is P1 V1 is equal to T, or divided by T1 is equal to P2 V2 T2. And again, this is sometimes referred to as the combined gas law. Now, in terms of pressure here, once again, it can be any unit you like as long as they are the same. Same thing here with our volume. And like every other gas law, temperature also here obviously does need to be in Kelvin, like we talked about. This is the one that sort of gives people a very difficult time rearranging going on. So, again, you might want to take a moment or two just to make sure you know how to properly rearrange each of these equations. This is also a really good one to memorize, if you will, because really from this one, you pretty much can get all the other gas laws that we talked about. So, go backwards here. So if we take our P1 V1 over T1 is equal to P2 V2 over T2. And essentially, all you have to do is take out whatever is being held constant. So if you have a problem where it's just pressure and volumes given to you, no temperatures, you simply just take out the temperature there, and now you have basically Boyle's law. If you have a problem where you are given everything but some volume, for example, you just take out the volumes, and now you have the Guy-Lussac's law. If you got something where you have constant pressure going on, once again, you just take out the pressures, and there's Charles' law. So it's a really good one. You can pretty much get almost every single gas law that you need by really just taking out the thing that's either not given to you or held constant, and then you'll get back to all those other sort of gas laws. Any questions on that one there? So why don't we try one here? See how we do. Consider a sample of oxygen gas at 27 degrees Celsius, volume of 9.55 liters. It has a pressure of 2.97. We change the pressure to 825 atmospheres, and we heat it up to 125. Calculate the new volume of the gas. Let's take a look. So once again, we pull out the information. We got a temperature that is 27 degrees Celsius. It has a volume of 9.55 liters and a pressure there of 2.97. We have another pressure of 8.25. We also have another temperature there of 125 degrees Celsius, and we are looking for volume. Once again, this should definitely point you in the direction of the combined gas law. We do need to actually adjust the temperatures on this one. So 273 gets us 300 Kelvin, and 273 gets us 398 Kelvin here. This case, we got P1 V1 T1 is equal to P2 V2 T2. Again, basically, we want to isolate our V2 by itself, which means everything else on the right-hand side needs to go to the other side. So our T2 will go to the top, and our P2 will end up over there on the bottom. And that will get you P1 V1 T2 over T1, and P2 is equal to our volume. So we're basically multiplying the T2 to both sides and dividing the P2 to both sides is basically what we're doing there. At this point, we want to put everybody in the right spot there. So that's P1, which is 297. Our V1, which is 9.55 liters, and our T2, which is 398, should go up on top. Divided by our T1, which is 300 on the bottom, and our P2, which is 825. The Kelvin on the bottom and top will cancel. The atmospheres on top and bottom will cancel. That leaves us just liters, which is what we're looking for, which is a volume. So that is a 9.55 times a 297 divided by a 300 divided by 8.25. And gets us maybe a 4.56 liters in this particular case. Any questions on that particular one there? All right, we will stop there, I think, for today.